Hello scientists, we're here to do the Unit 3 test review, and I just want to remind you, when you are taking the test, there's no notes, no help, no online material, and I am not kidding. Academic integrity is very important to us here at MNVA. Let's talk about vectors. Vectors have a magnitude and a direction. We know which way the force is being applied, or which way the velocity is going, and we know the size. So if you guessed speed and direction, you're absolutely correct. Pick the vectors out of this list. Pause the video for a second and think which of these quantities or descriptions are vectors. If you guessed velocity, because that by definition is speed and direction, if you guessed acceleration due to gravity, because we always know the direction of gravity, it's towards the center of the earth, and meters per second north, you are correct. This is a speed and a direction. North is a direction. Let's remember a force is a what or a what. I gave you a little hint here on some airline exit directions. You might remember a force is a push or a pull, and you might have to do both things to get an emergency exit on an airline door open. An example of a fundamental force would it be speed, velocity, acceleration, or gravity? Well, all those quantities are measured. Gravity is measured too, but gravity is fundamental. It's always the same if you're on planet Earth. Well, it's slightly different since there's a bulge here, but mostly it's the same on planet Earth. An example of a fundamental force is, of course, gravity. Velocity, you need two other measurements, same with acceleration, and speed, you don't know the direction. Gravity's pull is based on an object's what? An object's speed, an object's velocity, an object's acceleration, an object's force, or an object's mass. Both of these objects exert gravitational force. However, this one, planet Earth, exerts more because it has a larger mass. If you watch the TED-Ed video on how to think about gravity, you're aware that everything exerts a gravitational pull, but the size of that gravitational pull is dependent on the mass. Therefore, the feather doesn't exert as much mass. What does mass times gravity's acceleration, assuming we're on planet Earth, or a planet in general? Mass times gravity is going to equal your weight. Now your weight will change if you go to a planet with different gravity. Your mass won't. The more mass you have, well, if you add mass, if I pick up a small child or pick up a dumbbell and I get on the scale, what's going to happen? Is it going to read more or less? Hopefully you all guessed more. If you have more mass, you're going to weigh more. We all know that after Christmas when we've had too many cookies. On the moon, what happens to your mass? Do you have less mass on the moon? Do you automatically have less of a gut if you're this guy, if you travel to the moon? Do you have less matter? Nope, it's the same. But on the moon, what happens to your weight? You don't lose matter on the moon, but you do lose weight because that's due to gravitational pull. And if the gravitational pull of the moon is different, your weight's going to be different. You can see here that gravitational pull on the moon is less, therefore you weigh less. Your mass here is the same. Check out the astronaut here and the astronaut here, same astronaut, same mass, but the weight is 1,200 newtons here on Earth and only 200 on the moon. The moon is smaller than the Earth and therefore has, well, if you have less weight on the moon, therefore the moon must have less gravity. It has less mass, less gravity. You can see the vectors here. This one's a lot shorter. If the moon is, and this actually is incorrect, the moon has less gravity. The moon is smaller than the Earth and therefore has less gravity. That means you would weigh less on the moon. We just talked about that. You weigh less on the moon because it has less gravity, and it has less gravity because the moon has less mass. You have the same mass on the moon, but the moon has less mass than the Earth. So if you go to the moon and you drop your cell phone, there's less gravity on the moon, so the acceleration due to gravity is less. Is your cell phone going to fall faster or slower? Or at the same speed as here on Earth? It's going to fall slower because acceleration due to gravity is less if gravity is smaller on the moon. Remember, the moon has less mass, so it has less gravity, so things fall slower. You have more time to make a save and catch that phone before it hits. What else does the force of gravity cause besides weight? Take a minute, pause the video, and pick from this list what gravity causes. Were you correct? Gravity's pretty handy in keeping everything in orbit. It causes acceleration. It causes things to speed up and things to free fall. Draw in the gravity vectors. We don't need this here. If this is the sun, this is the Earth, and this is the moon, what's going on with gravity here? Take a minute, think about it. How would you draw in the gravity vectors? There's gravitational pull between the sun and the moon. There's gravitational pull between the moon and the sun. These arrows should actually not be equal in size because the moon is pulling on the Earth with less force than the Earth is pulling on the moon. The Earth has more mass, so it has more gravitational pull on the moon. And there is actually gravitational pull between the sun and the moon as well. What force slows things down? If you guessed, it's friction, because that's why we put tires on our car. Well, it's one reason we put tires on our car. You're absolutely correct. Here's a free body diagram that's showing why this box doesn't just take off and slide down the ramp due to gravity. It's because friction and the force due to gravity, the downward force this way due to gravity, the component is they're even, or the friction is greater, so the box doesn't move. Friction is good because it keeps you from running into people, and your brakes have friction, and that is a good thing. Your brakes have kinetic friction because the wheels are moving when you apply the brakes. Fluid friction is what happens when you go swimming. It would be more friction if you're swimming in a different liquid, a thicker liquid. You went swimming in corn syrup, you'd have even more fluid friction. If static friction is what keeps things in place, that are just sitting there. And rolling friction is if you're using wheels. So if you guessed, that is correct. All right, let's talk about free fall. Gravity influences an object in free fall. An object in free fall is influenced only by the force of gravity and accelerates downward at the rate of 9.8 meters per second here on Earth. Air resistance is the only thing that changes how an object falls. Gravity accelerates everything at 9.8 meters per second. So a 1,000 kilogram mass would hit the ground at the very same time as a 1 kilogram mass if there was no air resistance here on Earth. Galileo Galilei first proved that all objects free fall at the same rate. Galileo dropped balls of different masses from the Leaning Tower of Pisa, demonstrating that mass does not influence how an object falls. If a feather and a car at the same time fell off a bridge at the same time where there is no air resistance, which will hit the ground first? Remember, there's no air resistance to slow the feather down. They will hit at the very same time. Remember, this doesn't happen on Earth because we have air resistance and that kind of messes with Galileo's correctness. It's only air resistance that keeps the feather from hitting the ground at the same time. Let's go look at an example of something where there is no air resistance. So this is a video of an astronaut, and he's going to drop two objects, a feather and a hammer, and we'll see what happens.
Place to confirm his findings on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
You'll notice that they did hit the ground at the same time because there's no air resistance on the moon. Here on Earth, you understand a lot about air resistance because if you have two sheets of paper that you want to chuck into the recycling, you know if you just throw the sheet of paper across the room, air resistance is going to be a huge factor. It's not going to travel very well, and it's going to kind of float down like this as it encounters all of the air molecules. If you take the same size piece of paper with the same mass, but you change the amount of air resistance by changing the surface area, now it's going to fall at a much more predictable rate or fly through the air as you propel it in a much more predictable way because you've changed the surface area and reduced the air resistance. So air resistance is important on Earth, but the gravitational pull is the same for both pieces of paper. If we dropped both of these on the moon or somewhere where there was no atmosphere, so air wasn't an issue, they would fall at the same rate. That's it for the Unit 1 test review. There is no Part 2 for my class. I rolled it into Part 1, so just go ahead and do it at the end of Part 1. Thanks so much, everybody. Thanks for watching. We'll see you next time.